uh,
to the class children. Good morning, everyone. Good morning, guys.
Good morning, sir.
Okay, so few announcements from since it has been, we have received a mail that we need to conduct offline classes. So the classes will start from 10th onwards. So on 11th, we will meet at NR 313. In Nalanda. I hope you guys have received the mail. So we will meeting on NR 313 from 11th March onwards. And all of you need to be there so that we can conduct the offline class. Okay, this is one announcement. Second announcement, I believe you have already received that your class test will be offline. So I would suggest you start preparing hard, solve as many problems you can from the book. Now coming back to transportation problem, one interesting thing that needs to be noticed. So we started with G equals to 520, right? We started with G equals to, let it go. First iteration. So we started with northwest corner method with G equals to 520. Okay, let's look at, even without calculating, multiplying everything to find the G value, how can we directly find the G value? The next G value we got was 475 and G star we got as 435. So first iteration and then the second iteration, we got the solution. We started with northwest corner method. I will call it 0. This was the initialization. Now look at the reduced cost, which I have said. Reduced cost is nothing but Dj minus Cj, 0th row value. So we had 9 here. And theta, how much the value of theta we got for this one? 5. Remember it? Theta comes out to be 5. So we just need to reduce our G value minus 5 into the reduced cost value, which was 9 for, at that time, it was a non-basic variable. How much do you get? Just check. 520 minus 5 into 9. 5 is the theta, the basic variable. When we become a basic variable, theta was equals to 5 and 9 was the reduced cost. So 9 into 5, 45, 520 minus 45 equals to how much? Is it that difficult mathematics? Tushar, are you trying to say something? Am I audible?
So 475.
475. That is your first iteration value. In the first iteration, when you did the iteration, your theta came out to be how much? This was 4 and theta comes out to be how much? So your reduced cost was 4 and theta comes out to be equals to 10. So 475 minus 40, 4 into 10, that is 435. So using reduced cost, you don't need to multiply 2 into 15 plus 3 into something to get the G value. You can directly find it using the reduced cost and the new assignment value, what your G will be. Clear? Any questions? Now, let's see how this formulation is actually that whatever you have done in the table relates with the LP formulation of transportation problem. So let's start with, we already have formulated it, minimize summation I and j Cij Xij such that summation I Xij equals to, sorry, summation j Xij equals to Ai and summation I Xij equals to A, sorry, B subscript j. Good so far, and all Xij's are definitely greater than or equal to 0. Now, if I attach a dual variable ui and vj with this one, can you give me the dual formulation for this problem? Give me the dual formulation for this problem. How do we create dual, guys? Devika, how we can create dual for this problem? If I assign ui as a dual variable for supply constraints and vj as dual variable for demand constraint. Keeping silent won't help anymore, right? You have to come to a live class. So rather discuss it with me, try to clarify your doubts. Anyone? Very good. So maximize W equals to UI. So there is one variable everywhere. So it is nothing but summation AI into UI I equals to 1 to M plus summation J equals to 1 to N B subscript J B subscript J. That is your dual objective function. Simply we multiply RSS with the dual variable such that UI plus Vj minus Cij less than equal. So everywhere I have 1, 1, 1. So respective dual variable becomes, suppose u1 plus v1 equals less than equal to Cij, right? Cij is your cost coefficient. Now, what is the sign of ui and vj, the dual variables? How do we define the sign of dual variables? If we have equality constraints, what is the corresponding dual variable sign?
Unrestricted.
It will be unrestricted. So if you go back and see this ui and vj's which you have find, it can be any sign, positive or negative. Keep that in mind because that are nothing but your dual variables. Okay, now coming to, I was talking about the reduced cost earlier. So suppose if this is your zeroth row equation, x1, x2, x3, x4, x5, I'm just showing 5. So the one which are basic variable, what would be the value? The one which are basic variable, what would be the value in the zeroth row? What would be the coefficient in the zeroth row for basic variables? God, you guys are making it very difficult to teach. You are not responsive. I don't know what you are doing. Anyway, if this is how you want to proceed, I'm really getting irritated now. So suppose x1, x3 and x5 are your basic variable. Their coefficient will be 0. And these will have some numbers, suppose 9 or 5 or something. So this 9 or 5 is known as, for non-basic variable, coefficient, or more precisely what you are doing is Gj minus Cj. If you look at the revised simplex, so whatever Gj value is minus the Cj. So this non-variable coefficient in the 0th row is called reduced cost. What it means is, if I want x2 to enter the basis, how much I need to reduce this coefficient? If I want x2 to enter the basis, it should become negative, right? So that is the idea of reduced cost, and that is what we are following, ui plus vj less than equal to cj. So ui plus vj is equal to cij for basic variable, because ui plus vj minus cij, that is nothing but your this row should be equals to 0 for basic variable. For non-basic variable, we are calculating ui plus vj minus cij, and the moment it all becomes, because we are talking about minimization problem here, all of them becomes negative, we say we have reached the optimality. Otherwise, as long as ui plus vj minus cij is positive number, we keep iterating. So that is the, if you look at the table, this is what we call it transportation simplex, the UV method. Transportation simplex. So it is actually a simplex algorithm, only the representation wise we represent it little different. Understood? Any questions? Or for you to remember, reduced cost is nothing but your CB B inverse A minus C for the original variable, and CB B inverse for your the 0th row, which we write in the revised simplex form. Now we will look at different special cases in case of a transportation problem. Special cases in transportation problem, as we have seen in LP simplex. So first case is called degenerate case. So when do we say a solution degenerate? When one or more basic variable value is equal to 0. So if you remember the one of the solution which we got for least cost, in fact VAM also, I will just write that up to discuss at that point. For the problem which we have solved earlier, one of the cases, if you remember, which I doubt, were given the costs here 10 to 20, 11, 12, 7, 9, 20, 4, 14, 16, and 18. Okay, the assignment which we got for this one was 15, 5, 15, 0, 10, and 15. We have got 15, 25, 20, sorry, 5, not 15. 5, 10, 5, 15, 15, and 15. So you see, one of the basic variable was 0. So this is a degenerate solution. You have to mention it if you find something like this. This is a degenerate solution. Next one is multiple optimal solution. Second case, if you get multiple optimal solution. So suppose when you are solving a problem and if you get something like this. Okay, in simplex, how do we use to recognize the multiple optimal solution, guys? In simplex table, how do we recognize the multiple optimal solution? To suppose allocation which we have got 15, 15, 25, 25, 15, and 20. Suppose this is the allocation you have got and 15, 15, 25, 25, 15, and 20. Give me the values of starting with u1 equals to 0. Find the value of u2, u3, v1, v2, v3, and v4. Go ahead, find this. Find what values you get for u1, u2, u3 and corresponding the reduced cost for each of the non-basic variable. So you need to find u1, u2, u3, v1, v2, v3, v4 and corresponding reduced cost value for this assignment. Let me also put 20, 50, 35, 15, 30, 25, and 45. So you can see it is a balanced transportation problem. Try to find u1, u2, u3, v1, v2, v3, v4. God. We found the value of e1, e2, e3. V1, V2, V3, V4? Alpan Sen, can you hear me? Alpan Sen? Arnav Mandal?
Yes, sir.
Tell me the value of U2 and U3. Good, very good. You have found the values? Ades Dalwar? Okay, I will not tell you how to do it. You will find one of the, if this is how your response is towards every time I ask you something, then I'm getting really irritated. One of the non-basic variable coefficient or reduced cost value will be equals to 0. That shows that your gth row, one of the non-basic variable xs is 0. So you know this is a multiple optimal solution. Force it to enter it. Force it to enter the solution, you will find the other solution. Third case is, instead of minimization, if a maximization problem is given to you, I'm not going to ask any questions to any guys. I will just teach it as it is. I don't care. If you don't care, I do not care. So suppose instead of minimization, the problem is given to you. Suppose maximize profit. So instead of giving minimize cost, the profit is directly given to you. One such case could be X, Y, Z, A, B, C, D. Suppose this is what given to you, and profit of shipping 1 unit of product from X to A is given, X to B is given, and so on. So suppose this is what is given: 12, 18, 6, 25, 8, 7, 10, 18, 14. This number 14, it cannot be 11, 11, 14, 3, 11, and 20. Other values are 200, 500, 300, 180, 320, 100, 400. So you have been given profit per unit for shipping product from warehouse I to customer J. So I will take value of X, Y, G, and J will take the value of A, B, C, D. Okay. So what we have learned so far is for the problem of minimization, how we solve this. So the question is, what if we are given a maximization problem instead of that? So to solve such problem, what you need to do is find the largest value in each row. Not each row, in the entire table, find the largest value, find the largest profit coefficient and subtract all other cells with the from the largest value. So suppose in this table 25 is the largest, we will make an equivalent table. X, Y, G, A, B, C, D. I will subtract each one of them from 25. So we'll get 25 minus 12, 13, 25 minus 18, 7, 25 minus 6 is 19 and 0. Similarly, 17, 18, 15, 7, 11, 22, 14 and 5. Now we will solve this problem as a minimization. Now we'll first convert the table from a maximization to minimization table, and then we will follow whatever we do, whatever we have learned the transportation algorithms. So as you can see, this is the highest profit. I want to allocate as much possible. When I'm trying to minimize, this is the lowest cost. So if I assign it, I can easily work with. So just to show you what exactly has happened, suppose the problem I had was G equals to double summation Cij Xij. Cij here, however, was my profit. I was trying to maximize it. When I say that I will subtract each Cij from highest or max of Cij, what exactly we are doing? So G equals to summation Cij Xij. In this case, we have done summation 25 minus Cij, right, into Xij. So each of the value, I'm subtracting it for 25. Now summation 25 Xij minus summation Cij Xij. Since 25 is constant, I can take it out. Summation Xij minus summation Cij Xij. Now this is, we already know summation of all the Xij over I and J is equals to your either AI or Bj, whatever value you want to take. So this will come out to be either AI, some of the AIs, or some of the Bjs, whatever. So ideally this number becomes a constant minus summation Cij Xij. So equivalently, since it is a constant, we can ignore it when we are trying to maximize or minimize the problem. So we are getting G equals to minus summation Cij Xij, which is, since it is a maximization, I multiply with the minus, it is nothing but minimize G equals to summation Cij Xij. So this is the equivalent formulation which we are trying to solve. Now the last part of transportation algorithms. So far we have worked with balanced transportation problem. Minimize Cij Xij summation Xij equals to AI or summation Xij equals to B sub Cj. So this was my balanced transportation problem. And because of balanced transportation problem only, we were able to make all the algorithms which we have seen. Now, in real life, not necessarily you have an abundance of supply or abundance of demand. So let's look at the unbalanced transportation problem. So there are two cases possible in which you will have an unbalanced transportation. First could be supply is less than demand. Second case could be demand is less than supply. So let's look at, suppose I have three warehouses, W1, W2 and W3 at two markets, M1 and M2. Okay, this is the problem given to us. These are the difference cost given: 80, 215, 110, 108, 102.68. Okay. The demand and supply that was given to you was 2300 here and 1400 in this place. Demand was 1000, 1300 and 1200. So as I have told you, whenever you start solving such problems, first check whether demand is equal to supply or not. Because if it is not equal, you cannot use any of the algorithms which we have learned so far. So this is 13 plus 12 is 2500 plus 1000 is 3500, and this is 2300 plus 1400, 3700. So you can see your supply is 200 units short. In this case, although I would have loved to discuss with you, but since you have decided to keep silent, we add a dummy supply point. So we assume that there is a dummy, although it does not exist, but we assume that there is a dummy warehouse which can supply that much. So we have to give 200 supply. We can give 200 extra demand that is required from this dummy warehouse. Although this will not exist in practice, but since to use any of the transportation algorithms, I need to balance it, then only I will be able to use transportation algorithms. So we add a dummy source or warehouse, whatever you want to say, and its supply equals to total demand minus total supply. So in our case, total demand is 3700, total supply is 3500, so equals to 200. So I have, when we solve this problem, we will solve ideally for W1, W2, W3 to market 1 and 2. There will be shortage, but when we are looking at the problem, we do not know which market I will not which market I will not supply everything. To know that, we have to give this 200. And the cost factor for these two will be equals to 0. The reason being, I want this 200 to be allocated to one of these so that I know this much of demand I will not be able to fulfill for that market. So that's why cost will put it as 0. Now when demand is greater than supply, same thing, we add a dummy demand or dummy market, and its demand equals to total supply minus total demand. So let's say another problem. We have W1, W2, W3 and M1, M2. Right now I'm not, I have added dummy here, but original problem will not show dummy. You have to add it. So 1000, 1500 and suppose 1200. And your demands are 1900 and 1400. If you add them, this comes out to be how much? 19 plus 14 is 1 to 3300. This is the demand. Supply, however, is 15 plus 12 is 2700 plus 1000 is 3700. So I have 400 units extra. Now I do not know when this problem is there. Suppose when there is no dummy row, dummy column, I do not know which warehouse I will keep this 400. So we'll add a dummy demand column and put a cost equals to 0 so that remaining 400 should be allocated somewhere over here. And we know that at each warehouse, how much extra supply which you have, you need to keep it. So that is for your unbalanced transportation problem. So once you have balanced it, like suppose now I have added 200, it is balanced. Now I have added 400, it is balanced. I can use our Northwest Vogel's approximation least cost to start with, and then finally solve it. Now, if you remember, I told that this is, although we call it as a transportation problem, but it does not mean that every problem that is related to transportation can only be, formulated as transportation problem. The name transportation problem comes because of the special structure of LP, which I have already shown. So what I'm going to do, I'm going to give you a example of production planning that can be formulated as a transportation problem. So alternative formulation of production planning LP as a transportation problem. So there are many problems which can be formulated as transportation problem rather than an LP problem. The benefit is you can use heuristic to solve them. That is the benefit you have. You don't like you already seen that you do not need to worry about the artificial variable techniques and all if we can solve it easily. So let me write the problem. Suppose Swiss gear manufactures. We have already formulated this problem as a LP when we were discussing the LP formulation. So this question we have formulated as an LP earlier. Now we want to formulate it as a transportation problem. When I say transportation problem, what is required is you define what are the sources, what are the destination, and give a table of the cost. So this problem, there's this backpack manufacturer switchgear. So it has demand for next 4 months, March to June, as 100, 200, 180, and 300 units. Okay. Company uses part-time labor to accommodate the demand fluctuation, so they do not need to keep the same amount of labor. Some fixed employee and some part-time. Also, it has estimated that it can produce 50, 180, 280, and 270 units in March to June. That is, with whatever they have right now, they can produce this much. Now, a current month demand can be satisfied in 3 ways. Either you produce, like in the first month, you produce 50 and you supply to the the market. Second month, you produce 180, supply to the market. Second one is, the other way is surplus production in the earlier month. So suppose in the first month, the month of March, the current month demand is only 50. Why not produce more? So every unit of backpack which you produce more, you have to keep it in the inventory as 50 paise per pack per month. Okay. So suppose if I produced in March 50 extra bags, then if I'm selling it in April, then I am holding it for 1 month. So 50 into 0.50 rupees. If I'm selling, even I'm not even selling them in the current month, I'm in the month of April, what we are doing, we are still holding it. We'll sell it in the month of May. Then 50 paise plus 50 paise, 1 rupees extra. So 50 into 1. So this is how surplus production is done. So keeping the inventory. Third way is, which is also called back ordering. Many of the industrial engineering students will study this in production planning and inventory control. Surplus production in the later month. That means I could not fulfill 50 demand for March. I only produced 40. So 10 was the number of units which were left for demand for March. What I will do, I will produce this 10 in the month of April, and then I will send it to the customer. But customer will penalize me because I have satisfied the demand late per pack per month. So suppose 10, suppose in the month of March, I only produced 40 bags. I had to produce 10 more for March, but I'm producing it in April. So 10 into 2, 20 rupees extra it will cost me because of production. So you need to formulate it as a transportation table. So when we say a transportation table, you have to give, whenever I say that formulate it as a transportation problem. When we need something like this, there will be sources, there will be destinations, and you have to give the cost of the each month. So this is what needs to be done. So you think about it, solve it, and we will discuss it next class. And as I said, keeping silent is not helping. Until unless you discuss with me, I won't be able to clarify many doubts you might have. So it's up to you how you want this to proceed for next 1 month. But anyway, on 11th, we are meeting at Nalanda in NR 313. Let me just confirm it is NR 313. NR 313 Nalanda. It is after the, if you cross, you don't need to go to the subway side. On the road on which agriculture engineering is there, if you just go ahead, there is an entrance to Nalanda. On your left, not on your right, you will find NR 313 on the 3rd floor. I believe you do not have any questions, so there is no point asking if you have any questions. So I will see you guys on Friday at Nalanda in Nalanda at 11 a.m. Thank you very much.